goal of today, let's get back to the lectures. Goal of today is talk about learning, which is really one of the shorter units. And so I hope to get through everything I plan to talk about with regard to learning. And there's a few major themes, right? And then I want to move on to language, because I really think of the learning literature as very closely intertwined with the language literature. And so here, I'll just go over a few of the theories of learning, and this starts from molecular levels of theories all the way up to more cognitive kind of debates that are ongoing right now. We'll talk a little bit about the neural substrates, and of course learning and memory. There's a course on neurobiology of learning and memory, and there's a course on psychology of learning and memory. We'll talk about the neural substrates of both, right? And you'll see how the work on learning is a little bit like a logical extension of the work on memory, which we've already talked about just before the test. We'll cover a couple of the general paradigms and findings from those paradigms, and then we'll talk about some of the learning disorders. A couple of common ones. The most common one is dyslexia, right, which is a problem with learning to read, and then dyscalculia, which is more a number-specific calculation deficit. So theories of learning, and this gets back to kind of the beginning of the cognitive revolution. Recall on the very first day when we talked about how Edward Tolman came around after the behaviorists and the neuroscientists. Edward Tolman came and said, well, it's not just, the brain is not just an input-output mapping system, right? We have cognitive cognition, which is really a representation of knowledge, an internal representation of the external world that's inside our minds, and these cognitive operations matter, right? And that's really the core of cognitive science, is trying to understand where knowledge comes from, right? What knowledge is like in our minds. And the nature-nurture debate in cognitive science is about to what extent you're born with knowledge, right? And this is something that modern cognitive scientists are still debating. It's one of those questions that never seems to find an answer. And of course, the right answer is probably somewhere in between, or both sides have some merit to it. But it's there are some people we call nativists who really think that you're born with certain types of knowledge. In other words, you have innate knowledge. On the other hand, you have people who really embrace the nurture side of things, right? Who are born, and the extreme end of this, you would say that people are born with no knowledge or a blank slate, right? And then and everything that you know is based on experience. So, and of course, again, truth is somewhere in between. But we know that there's a lot of neurobiological mechanisms that really show how learning happens and gives rise to memory, and then that memory is encoded as what we call an engram, which is actually the code, memory code itself, and then that memory gets consolidated over time. And the last time we talked about long-term potentiation, or LTP, which is a mechanism that happens within the specific cells of the hippocampus. Right? So recall how we had the dentate gyrus that talks to the CA3, that talks to CA1. This is a three synapses that are specifically in the hippocampus. And these cells in the hippocampus, when they fire in volleys together, this creates a long-lasting potentiation. And so the short way to say that, cells that wire together, wire together. Cells that fire together, wire together. And so that's really illustrative of how plasticity might occur. And it turns out that if you look at infant rats, right, they show a different pattern of long-term potentiation in the hippocampus. And this corresponds quite well with the ability of young rats to learn certain skills that adult rats cannot. Right? So this is what's called the critical period, or the sensitive period. The idea that you have certain windows of opportunity in your brain, right, that are characterized by better plasticity. Right? So long-term potentiation and plasticity, these are things that can change over time that then give rise to sensitive periods in learning. Then learning is not, there's not only one way to think about learning. Right now we're doing a pretty explicit form of learning, right? So I'm standing here and lecturing to you. It doesn't really get more explicit than that. And your job is to take all this explicit knowledge and like learn it, and then come back and show me that you've learned it by doing well on a test. But much of your life is actually not explicit learning. It's more implicit learning, right? So learning how to ride a bike is a pretty classic example. But another very classic example is learning things like grammar in your language, right? So if you're a first language English speaker, you don't have to be told that the word the is the most common word in the English language. You just know it, right? So these are implicitly learned information. So grammar is a very classic example. And then also another form of implicit learning is something that you can gain from practice. So such as using language or riding a bike, right? And then there's lots of work on the effects of practice on implicit learning. Generally, if you show that, people are generally showing that if you practice in distributed amounts over time, that works better than if you're just doing massed practice. In other words, one large bout of practice at a time. Right? So, and that relates to the work on forgetting. So forgetting curves, you can look at how quickly people forget information that's told to them or that they're exposed to over time. And it turns out that if you distribute the exposure over time, you're better at it compared to if you kind of crash or crammed just before the test. Okay. Then we also talk a little bit about motor learning, which is another form of implicit learning, and that's assessed using the serial reaction time task. It turns out that you can form certain grammatical structures within the serial reaction time task that can help you probe implicit learning. Right? So think of motor learning using serial reaction time tasks as very related to this idea of grammar and implicit learning. And then it seems like every major term these days has been kind of co-opted by neuro and then whatever. So if you're interested in economics, there's the whole field of neuroeconomics. And it kind of pains me to say this, but if you're interested in education, there's this whole new field of neuroeducation that is trying to capitalize on these topics like synaptic plasticity and working memory and kind of long-term potentiation. These kinds of ideas, trying to translate those into the classroom. So what might that look like? Nobody really knows, but it does look like a lot of work on brain training. Right? That's kind of been a hot topic for the past 5 years or so, are really starting to get translated into the classroom. So there are a couple of schools that actually now tend to be more kind of forward progressive thinking types of schools, have a couple of neuroeducators that are serving as student advisors, but also people who use sort of neuroscience theories to inform how learning in the classroom might occur. So that's a whole lot of kind of opportunities out there. But I want to talk about some themes that you'll see from today. One is that learning depends on the statistics of stimulus distribution in the environment. Right? So there's a statistical dependence of our implicitly learned information. In other words, we tend to learn frequencies and probabilities of the information in our environment, and that shapes our implicitly formed knowledge. And so what does that mean? We spent most of today on this, but just to give you a very nice example, I've already said that if you're a first language English speaker, you already know that the word the is the most common word in English language. So the frequency of the word the is higher than the frequency of any other word in the English language, right? So the English language is statistically dependent. Right? So it turns out that kind of statistics, or our brains are very good at computing these statistics, and the ability to compute those statistics depends on a cortical network, especially centering around the basal ganglia and the hippocampus. And we'll talk more about those basal ganglia. And the hippocampus and how they interact to help learn the statistics of environmental stimuli. Now, So recall from the last day when we were talking about memory, we showed one example of implicit memory or implicit learning is the mirror drawing task. Right? So HM, right, who was our poster child, who had no explicit memory, right, couldn't remember anything that just happened to him, could nevertheless perform this mirror drawing task, which is one of the classic examples of implicit learning. So the implicit learning task, right, that entails a shape, and the subject is not allowed to look at their own hand when they're tracing the shape, but they are allowed to look in the mirror. Right? So there's a motor component to the task. And HM, it turns out, much like normal control subjects, show the decrease in the number of errors, which also mirrors a decrease in reaction time over the course of different trials, repetitions of this kind of task. Right, so he got a lot better at this over time. Now, this is one example of an implicit learning task. Another example is the serial reaction time task, right? Again, that requires implicit learning. Right? So the pattern, I mean, the general idea is, the setup is a little bit different, right? But the pattern of results is quite similar. Right? And in the serial reaction time task, you get these 4 different locations, possible locations on the screen, right? And the light would light up on one of those 4 possible locations, and you're supposed to press the corresponding button in your 4-button box. And so over time, of course, there are certain structures, right? So there are certain repeated sequences in your in the sequence of cues and targets that you're supposed to respond to. And so, of course, you get faster and faster over time. And such that when the researcher suddenly perturbs that sequence later on by giving you a random sequence, that shows you show a very sudden increase in reaction time again. Right? So this difference between the structured sequences versus the random sequences, there's a difference in reaction time, and that maps on quite well to implicit learning ability, which then maps on quite well to differences that are observed in the basal ganglia. So this is kind of a blurry image of a bunch of activity in the basal ganglia. So let me just show you a little bit more specifically where the basal ganglia are. The basal ganglia generally include 3 nuclei, 3 gray matter areas that are subcortical. Right? So generally, the brain has more gray matter at the level of the cortex, or at the outsides of the brain, but more white matter on the insides. But this is different for the basal ganglia. The basal ganglia are a set of gray matter areas that are subcortical. And those include the caudate, right? So the caudate nuclei here, which are sitting right underneath the ventricles. And then the putamen, right? And then which are these lightish blue areas right here. And then within the more mesial to the putamen, you have the globus pallidus. And there's internal and external segments of the globus pallidus. So caudate, putamen, and globus pallidus. These together are known as basal ganglia. They are also known as striatum. And so I'll just write that down, actually. Just think of striatum and basal ganglia as the same set of areas. And so I'll use them interchangeably. But just know that when people are talking, the people who study motor functions and learning are more likely to call it basal ganglia, and the people who study reward and dopaminergic system are a little more likely to call it the striatum, but there's really the same set of areas. But what we know is that the basal ganglia are really important for the formation of habits. Right? So these are what the basal ganglia are doing are modulating these circuits that talk to the cortex. And why is that useful? Because if you're doing something repeatedly, you should develop a specialized set of circuits to enable that. Right? So think about one set of habits. Right? So throughout the course of the semester, you learn your schedule, right? your class schedule, and so it becomes very, very automatic that every Tuesday and Thursday at 1:20 you want to be here. Right? So that's a habit that you've hopefully formed over the course of the semester. And so the basal ganglia basically adapts to those habits, such that if you suddenly have a perturbation or an unexpected event that forces you to break that habit, right? Let's say if one day it turns out that I said we don't have class, so and like somehow, so I said like don't come to class, but you have to use your cortex to actually override that loop, like that basal ganglia-driven circuit that you've already formed in your brain. So it takes cortical control to break a habit, and that's useful because when most of the time these habits are formed for a good reason, right? Because usually you are rewarded or you're doing the right thing by coming to class at the right time, right? And so you shouldn't need your cortex to keep constantly reminding you that you need to perform the habit of coming to class. Right? But in that off chance that there's a perturbation in the environment that forces you to break the habit, that's when cortical control needs to kick in. So in the lab, how do we test this kind of thing? We have some probabilistic classification learning tests, and so it's really just a very fancy way of doing statistical dependent learning. But it's couched here as the weather prediction task, and so where you're supposed to see a card, or you're given certain kinds of cards, and you're supposed to say whether you think it's going to be sunny or rainy. And unbeknownst to the subject, these cards are associated with different probabilistic outcomes for whether you will actually get a rainy or a sunny outcome. Now, and for every trial, right, you see a card, and you say whether you think it's going to be rainy or sunny, and then you're given some feedback, and you're told whether you were right or wrong. And so over time, people tend to become sensitive to these different probabilistic distributions. Right? So if this card, if 3/4 of the time this card shows up, it's supposed to be sunny. Whereas only 1/4 of the time this card comes up, it's supposed to be rainy. People will start to, people's responses will start to show sensitivity to that, right? So they'll, when this card comes up, they will be more likely to say sunny. This card will be more likely to say rainy. Right? So I think that's a very rational learning process, and this happens with unconscious, without explicit awareness. Right. So that's it's actually quite a simple task, but the implications are far from simple. Right? So if you think about language, like I've already said, language has lots of probabilistic information in it. So consider how a baby somehow has to learn, has this remarkable task of learning their first language. Right? And you might, if you see a baby, you might try to talk to it and try to teach it language, but it turns out that the babies learn language mostly from just being exposed to sounds and words. And so what might these statistics of language sounds look like? So let's say if you're a baby, right, and you're given this whole sentence, oh, what a nice baby, look at this pretty baby. It sounds like something you would say to a baby, right? So your system has to figure out what are words in your language. So you have to do the task of word segmentation, right, finding the boundaries between words. And so it can do so by looking at all the sounds and looking at transitional probabilities between each pair of sounds. So transitional probabilities just means the probability of one syllable given the previous syllable before it. So within this corpus, this very simple language that you've just been exposed to, there's a word that shows up twice, right, and that's baby. And so every time the syllable B comes up, it is preceded by the syllable bay. So the transitional probability of E given bay is quite high. And every time the word pretty shows up, right, every time you hear T, that's preceded by the word, by the syllable prit. So again, transitional probability of T given prit is quite high. Now let's look at between word transitional probabilities. Right? So you heard baby twice. The first time it's preceded by nice. The second time it's preceded by T. Right? So the transitional probability of babe given T before it is low. So essentially what we're seeing is that within word transitional probabilities are high, and between word transitional probabilities are low. And so if you have a baby that's just sensitive to transitional probabilities, it should be able to use this, just the transitional probabilities information to figure out what the boundaries are between words. So that's a really important and powerful idea, and that has been shown in infant studies from 1996 and a million of them onwards. And it maps on quite well to at least the word segmentation problem in language. Okay. All right, so what are some neural evidence for statistical learning? All right, so this is one example. Right, you can also do more artificial lab-based tests. This is a whole series of work on statistical learning now, where people were given triplets of different squiggles. Right? So think of them as glyphs, like hieroglyphs, right? And they're given these triplet structures in certain repetitive ways. Right? So that's essentially it's an artificial language with each of these different glyphs forming one syllable in language. Right? And so you can think of one word as 3 of these syllables happening next to each other. Right, so we've got a few different words here, 4 different words, and each of these glyphs belongs to one position. Right, so it always has to be in the beginning of a word, or the middle of the word, or the end of the word. And so people are given these structure blocks to learn over time in the kind of serial reaction time test, and then they're given some random blocks, and those random blocks compared against the structured blocks are what are a useful index of learning. And so when you contrast the structured sequences in the brain, so people are doing functional MRI, undergoing functional MRI, and doing these serial reaction time tests, and when you contrast structured sequences versus random sequences, you get firstly activity in the basal ganglia. So right here is the caudate nucleus, which is part of the basal ganglia. And then in addition, you get areas that are in the late visual system. So part of the occipital lobe, right, that are useful, that are showing this sensitivity. So a difference in activity between structured sequences and random sequences. So the brain is quite efficient at detecting these statistical regularities, and it seems to occur without conscious awareness. Okay, any questions about this? Okay. So, yeah. Yeah, so ventral, occipital, temporal cortex. You don't need to know this exactly where they are, but it's generally part of the late visual system. Yeah. Yeah, so what they've done is run a word localizer. There are all these, like, when you're doing functional MRI studies, you usually, it kind of depends on what camp you're from, but generally they do a localizer, which means you show people a bunch of different words, and you isolate the area of the brain that's sensitive to words, and you call that the word selective area, and then you look at how that area gets modulated. Localizers. We didn't really talk about localizers, but it's a kind of standard technique in fMRI land. All right, so let's move on. Any other questions? Let's move on to learning disorders. Right, so a couple of relatively common learning disorders. One is dyslexia, which is the difficulty in learning to read text. So a classic example is difficulty in spelling. So it's a learning disorder because it's in the absence of deficits in IQ or peripheral sensory processing, right? So these people are not deaf, right? They're not blind. They just have, and it's not just that they need glasses or hearing aids or something, right? So it's not a sensory processing problem, but it's something more central to that. And this is also not an IQ problem, right? So usually what a neuropsychologist might do is administer a battery of tests that assess phonological or phonemic awareness, which is your ability to manipulate speech sounds, in addition to some more baseline IQ types of tests. And so you would have to show that you actually have dyslexia, you would have to show normal IQ function and also a deficit in more reading specific functions. So the incidence is quite a range. Right? Some estimates are around say that they're around 17%. Other estimates are around 5%. The real number is really somewhere in between, but I should say that in developmental populations, you see more people with dyslexia, and then as children grow up, you tend to see a lot of children grow out of it, right? So you tend to see a decrease in this rate, in the incidence of dyslexia over development. So generally speaking, there's a few different theories behind the experiences of dyslexia. And some people talk about this as a kind of a different visual experience. Right? So some people who have dyslexia say that when they read text, it looks all scrambled to them. And so this is just an example of scrambled text. Some people say that when they're with their dyslexia, when they see text, it looks all blurry to them, right? Or it looks more spatially disorganized. And then there are other people with dyslexia who experience more auditory differences. Right? So I'll just show you an example of this. Hopefully it'll sound fine. Yeah. Okay. I just have to fiddle with this. Come on. Not sounding?
6, 2.
Okay, let's try that again.
8, 5, 4, 9, 1, 6, 2.
Okay, can you repeat the words that were spoken to you? Yeah.
8, 5, 4, 9, 1, 6, 2.
Right, so that's good, quite good, right? So this is a digit span task, right? So classic digit span task, you get told a bunch of numbers, and you're supposed to repeat them back. Right? And you're generally quite good at it, up to a certain number of digits, usually 7 digits, plus or minus 2 digits. Right? So the exact number depends a bit on your first language, right? If your language, if in your language it takes less time to say these words, then you tend to have a bigger working memory storage for digits. But what people with dyslexia tend to show is less ability to repeat back these digits. So the digit span is smaller. And one theory behind why this might be is that there's slower temporal processing in people with dyslexia. And so that means that even though their peripheral auditory functions are good, right, they can hear the words that are spoken to them, they hear it in a more temporally smush or with poor temporal resolution. And so what might that sound like? So here I'm taking the same string of numbers and just playing them back with a temporal function so that it sounds blurred over time. So it's quite striking, right? So you can still kind of hear the words, but the words are kind of smoothed over so that it becomes a lot more effortful or attention demanding to hear the words themselves or to resolve the words themselves. And so this is, it's an illustration of what a dominant theory for dyslexia is that the rapid temporal processing ability of the brain, which is part of the auditory system, is disrupted. So there are essentially two major views of why dyslexia might occur. And it could be that this, what we call dyslexia, is really just a grab bag of different impairments, some of which are more visual, others are more auditory, right? But and so the two classes of theories are visual and auditory, right? And so the auditory deficits include things like impairment in phonological processing, or phonology, which means the ability to manipulate sounds from your language in your head. And so if you have poor temporal processing, right, so such as hearing the digits kind of smooshed out in time, right, that's a temporal processing deficit in auditory processing, right, and that could lead to a reading impairment. So that's the auditory part. The other alternative is visual problems. Right? So when we're talking about vision, recall we talked about the magnocellular and parvocellular pathways, and that map on generally to the where versus what pathways. Right? And so it might be that the what pathways within the visual system are disrupted. Right? So both of these theories could give rise to a reading impairment, but through different routes. Yeah. Right, so it would show up quite specifically. It would be generally more taxing to do normal auditory processing. And then when your task is specifically to analyze sounds within words, you would end up with more specific problems. Right, so one classic example is, actually it's the next slide. Phonological awareness test, right? So this is the ability to manipulate speech sounds in your mind. Right, so phonology just means sounds of your language, and awareness means that you have conscious knowledge of these sounds in your language. Right, so one of these auditory specific tests, right, for dyslexia could be sound categorization. So, for instance, pick the odd one out between these four sounds: pat, bat, mat, and tap. Okay, who thinks that tap is the odd one out? Right, so that's quite, so you're able to tell that they all end with a T except for that last one. Right? So that's a sound categorization test. Now here, let's say auditory analysis test. That's another kind of phonological awareness test. Say cowboy without the boy. Cow. Right? So that's quite easy. But now, what about this? Say create without the E. Create. Right, and that's fine, but that's obviously a bit harder than just saying cowboy without the boy. So all of these tests require that you analyze the sounds of your language and then reconstruct them in some way, manipulate them in some way. And children, and this is pretty classic and well-replicated finding, that children with dyslexia are impaired at phonological awareness tests. And not only are children with dyslexia themselves impaired at phonological awareness tests, children who are siblings of children with dyslexia are also impaired at phonological awareness tests. So we know that there's a genetic component to dyslexia. So if you have dyslexia, there's a higher than chance probability that your sibling will also have it. So let's talk a little bit about evidence supporting both the visual and the auditory theories underlying dyslexia. Right, so one study comes from looking at the visual theory specifically, and it looks at how contrast estimates, how your ability to see contrast in the visual system might relate to your ability to do these phonological awareness tests, such as picking the odd one out in sounds and saying certain words without certain phonemes. So what do we mean by contrast sensitivity? Here we have a couple of visual examples of high contrast and low contrast. Right? So obviously high contrast is black and white, low contrast is different shades of gray. So you can construct these sinusoidal gratings that are just different shades of gray. Right? And you can make them high contrast, which is closer to black and white, or low contrast, which is closer to just a very fine-grained gradient of different shades of gray. And if your job is just to detect, right, whenever you see a grating, the higher your contrast is, the better you are at detecting these gratings. But everybody has a threshold, right? So there's a certain level of contrast required at which you start to reliably identify the gratings. So this is a very standard psychophysical task in vision. And what the Wandel lab at Stanford observed was that the area MT, as well as area Phi1 and Phi3, so these are part of the Ware pathway in vision, it's sensitive to these different levels of contrast. So as you increase the contrast, the higher the contrast is of these visual sinusoidal gratings, the more you get activity in the area MT and these other areas. And furthermore, then what they saw was that the slope of your activity in the area as MT and Phi3A and Phi1 was correlated with your phonological awareness score that was collected outside the scanner. So that means that the more sensitive you are to differences in sinusoidal gratings, the better you tend to be at saying create without the E, which is really quite wild, but it does provide some evidence for this relationship between visual processing ability and spelling. So that's a pretty good evidence for the visual system's involvement in dyslexia, I think. So now that's not the only functional MRI study that's been done on dyslexia, of course. This is just a snapshot of 34 different studies that are here meta-analyzed. Right? So we're looking at areas of the brain that are pretty consistently active from 34 different functional MRI studies that are showing differences between people with dyslexia and controls. And generally what we're seeing is not just visual areas, but also areas that are lateral, in the lateral temporal and frontal areas. So that includes areas in what we would think of as auditory cortex, right, in the superior temporal gyrus, and also areas that are more posterior to that, as well as areas that are in the frontal lobe. And the general finding is that these areas that, especially in the lateral temporal lobe, in the auditory areas, are correlated in their gray matter structure with the phonological awareness test. So here, rapid automatized naming, or RAN, is just another form of phonological awareness test, where I think of it as being a little bit like saying create without the E, but that ability is correlated with gray matter volume in the auditory areas. And furthermore, I think this is a really nice paper. I think that it also gets covered in some other classes. But these researchers from MIT looked at the role of white matter structure in the brain in predicting your ability to read as a child. So these are in this project, the researchers were looking at children who were pre-kindergarten, right? And so they haven't even learned to read yet, but they're related. They're siblings of children who have dyslexia. Right? So we know that just by genetically, these kids are a little bit more likely to have trouble, to develop trouble learning to read later on. And so it becomes even more important to catch them early on to do interventions if needed. And so what they found was that the path that's yellow here, it's the arcuate fasciculus, which is the major white matter pathway that's connecting the areas that are important for auditory perception in the temporal lobe, and the areas that are important for speech production that are in the frontal lobe. And we'll talk much more about the arcuate fasciculus when we talk about language, but this is a good view of them, the pathways that are yellow here. And what they're seeing is that the arcuate fasciculus is correlated in its white matter integrity. So fraction anisotropy, which is Fa, which is a correlate of white matter integrity, that was associated with these phonological awareness tests. So blending words is asked to put words together, right? So it's a lot like these phonological awareness tests that we just practiced. Right? So the blending word score was actually correlated with the volume and the fraction anisotropy of the arcuate fasciculus. So what they're showing is that it really doesn't matter whether you've already been taught to read. Right? So these are pre-reading kids. They just already show these inherent differences in ability to do phonological awareness tests, and those inherent differences are related to volume and integrity of the white matter in the arcuate fasciculus. So generally, we're seeing both auditory areas, right, including the arcuate fasciculus, and visual areas, including area MT, that are involved in dyslexia. Right, so again, that supports both auditory and visual parts of the disorder. Are there any questions? Okay. Right, so I want to talk more about dyscalculia now, or number processing. But before I talk about disordered numerical processing, I want to talk about normal numerical processing. So I'm going to show you very quickly I'm going to show you two pictures on either side of the screen. They're going to be a bunch of dots, and I want you to, as quickly as you can, point at the part of the screen that shows more dots. Okay, so there are two choices. Just point at the one that has more numbers. Okay, that has more dots. Okay, ready? Okay. Great. All right. So you shouldn't have to. So people are pretty quick at this, right? And you shouldn't have to go sequentially count every single one. You have to say 1, 2, 3, 4, 5, 6. You shouldn't have to count these in order to just estimate the relative numbers of dots on the screen, right? So you can tell, like, just by glancing, it looks like this side has more dots than that side. So you're using your approximate number system, so which is the ability to guesstimate not the magnitudes of numbers without knowledge of individual items themselves, without counting them, right? And so if you don't think that that's relevant or important for education, it turns out that individual differences in this nonverbal number acuity, or the ability to estimate numbers, actually correlates with math, with your PSATs. So how many of you had to take the PSATs before taking the SATs, right? So that's a common scholastic aptitude test, right? So it turns out that the PSATs scores actually correlate quite well with the nonverbal number acuity, with your approximate number system. And so another way to test your approximate number system is by these incongruency tests, and I'll show you one of these. So can you tell me which number is bigger? Okay, so some people are clear. Some people are confused. Why are we confused? Right. Okay. So is it, but when I say bigger, do I mean taller, just like occupying more space on my screen? Or do I mean that the numerosity is greater, that it signifies a greater value? Right. And so there's an incongruence, right? So I've purposefully juxtaposed a gigantic 3 against a tiny 8 because I'm juxtaposing the different cues. So I'm making the cues of height and numerosity incongruent with each other, right? So I can also make a congruent situation in which the smaller number is small and the big number is tall. And so this is now, there's no question now which number is bigger because the greater one is also taller. And so if I were asking you to answer the question which number is bigger, most people, normal people, show a size incongruity effect, right? So they're faster to respond when the numerosity is congruent with the height of the size of the digit, right? Compared to when they're incongruent, when the numerosity and the height are incongruent. So there's a reaction time difference, which is quite sensitive, it turns out, to your automatic number system, approximate number system. And so the underlying brain network, there's quite a busy slide here, but generally it's supposed to be a mostly left hemispheric process. And a couple of major hubs, they include the IPS, the intraparietal sulcus, which is part of the parietal lobe. And so this is you don't need to memorize all the areas of the brain that are listed here, but you just generally need to know that most of the areas that are important for arithmetic are left hemispheric, and especially there are some areas in the parietal lobe that are especially involved. And so the IPS stands for intraparietal sulcus, which is in the parietal lobe, and this is just a review article showing that when you're doing quantity processing, quite generally you see activity for humans in the parietal lobe, in the intraparietal sulcus, and then also in the analog of the intraparietal sulcus in monkeys. So people with dyscalculia actually don't show the size incongruity effect. Right? So the 3 versus 8, right, they don't have that reaction time difference in response to incongruity between numerosity and height of numerical digits. And this is correlated with, they also have difficulty learning numbers, right? Learning math, learning how to do mathematical operations in their heads. And this translates to all kinds of everyday difficulties in everyday life. Right? So not being able to use an Excel spreadsheet, but not being able to read a calendar, not being able to read a clock or make change when they're in a grocery store. So you can see how this can propagate and can be quite detrimental to everyday function. But this is, again, just like dyslexia, this is accompanied by normal IQ. Right? So these people don't have IQ problems, nor do they have peripheral sensory problems. Right? So it's not just that they need glasses or hearing aids or something like that. So this is a very nice function MRI study that made a very good control task for arithmetic functions. And so in the experimental task in the function MRI, human subjects had to do simple mathematical checks. And so you're given these examples of math equations that are either right or wrong. Okay? And as a control task, you're given these non-mathematical tasks where you're just supposed to look at some numbers and see whether they match. They're the same before and after the mask, which is in between your the cue and the target. Right? And when the researchers contrasted the experimental task of arithmetic verification and the control task of digit matching, what they saw was a couple of regions are quite consistently sensitive, especially the intraparietal sulcus, or IPS, in the parietal lobe, and areas in the dorsal prefrontal cortex. And then for further causal evidence that the IPS is actually related, another group then actually took in addition to using a functional MRI to define the IPS, they also took a TMS setup, right, and they actually zapped or stimulated the IPS on normal subjects who don't have dyscalculia. And essentially what they showed was that the subjects after TMS over the IPS no longer showed the size incongruency effect. So they no longer showed the reaction time difference between numerosity congruent and incongruent conditions. So essentially it can artificially induce a very transient form of dyscalculia by just zapping, right, stimulating the parietal cortex. Okay, are there any questions? Yeah. Mm-hmm. Yeah, so they stimulated both sides, but general finding was that the results were more for the left. Yeah. Okay. So in the remaining minutes, I think we got another 20 minutes. I'm just going to start a little bit talking about language, which is our topic for the next day. But I know that it's quite a large subject and there's a lot involved. So I just want to get through a little bit. And there's some interesting videos that I think will give you a nice sense of what language disorders look like. So yeah, so I'm kind of preemptively, I'm getting an early start on the language topic. Okay, so the outline, I'll talk about the anatomy. So the anatomy of language is really well studied, and so it's been studied since the 19th century. So I'll give you the 19th century model, and then I'll give you the 21st century model. And then basically I'll just go through all the major topics that neurolinguists, or people who study the neuroscience of language, care about. And so I'll start with phonology, which again is the study of linguistic sounds, and then go through syntax, which is how you put words together, and semantics, which is the study of meaning, pragmatics, which is the study of how you use language in your everyday life. And then people are always interested in what their brains look like when they speak multiple languages. So bilingualism is one thing we'll just talk a little bit about. But so today, hopefully I'll get through just a first few ideas about the anatomy of language. Okay, so brain anatomy of language. So this is a picture of Norman Geschwind, who was a 20th century thinker. And he famously came up with the idea of the language network. And this was in the 1970s. And this comes from the classic work by Paul Broca, whom we talked about in the very first day of this class, which is one of the classics of the Broca's aphasing, right? And then also the later work of Wernicke, and then some work of his own, Geschwind's own. So this simple three-node network model of language includes the Broca's area, which is B here, and that's in the inferior frontal gyrus. And so that's the inferior part of the frontal lobe. And the Wernicke's area, which is in the superior portion of the temporal lobe, superior and middle temporal lobe. And then there's an arcuofasciculus, which connects them. So I'll show you more pictures of those in a moment. But just let me show you a person with the classic deficit in Broca's area. And so this is known as Broca's aphasia. Okay. So it's actually quite a sad video. But it's a young person. Her name's Sarah, and she's 19.
So what's your name?
Scott. Oh, no. Sarah Scott,
That's right. And how old are you?
I can't.
Okay. All right, so yeah, you have a question? That's a really good question. Yeah. So there's a clinical trial right now looking at people with Broca's aphasia. And so obviously, I think the take-home points from this are that she has trouble finding words. Right? She really understands the conversation that she's having. She can hold the conversation, but she has trouble finding words, and it's very telegraphic in a way, right? So she's really using just the words that she needs. Takes a long time to find them. But the grammatical structure is pretty much not there. Right? So she doesn't say her ifs and her buts. She only says that the words that she needs. But the words that she eventually finds are very meaningful, right? So she can convey the meaning. So there's not much problem with comprehension of speech, but there's problem with word finding and word production, especially. And so so that's a really good question. So one effort is an ongoing effort is to use music, singing to help them recover. And it turns out that there are some of these patients are actually nevertheless able to produce songs, right? So they might say, so this is actually a pretty well recovered and good case of there are some people who can't form any words at all. So Broca's classic case, patient Tong, right, would just say Tong 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 all day, and there's some newer cases that I've seen where the patient would just say Tono 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 Tono, and so you could ask them, how are you today? Tono 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 Tono. There's like different pitches, but they're not forming words. So that's another case. Some other cases of Broca's aphasia. But it turns out that those people, some cases, if you ask them to sing Happy Birthday, they can actually sing Happy Birthday with the words. And then when you ask them to say the words of Happy Birthday, they just say Tono 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 Tono, which is really striking. But so that leads some people to think that if you engage them in singing, you might engage the contralateral homologs of the Broca's area, or so the right hemisphere inferior frontal gyrus might try to take over some of the functions of the left inferior frontal gyrus, which is the Broca's area. Yeah. Sorry, I can't think. Can they what? Right, so they can't learn language as well as people who don't have aphasia. No, I mean, it would be so easy if they could just. But the problem is deeper than that, right? It's not just about picking. It's not just about the output itself. It's more about the ability to string words together. Yeah, so the syntax of ASL would also be difficult. Any other questions? Okay, I think we'll just stop there today, and when we come back on Thursday, we'll talk about a little bit more about Broca's area, and then move on to Bernke's area and the rest of language.